All right, so we're going to pick it up where we left off yesterday, which is composite functions. This is kind of an interesting idea. What you actually have here is a case where we have a function of another function. So there's a couple of ways we can express these. You may have seen this notation before, f with this little zero here. I'm not sure what the proper name is of this symbol. But anyway, the way it's written is FOG. I personally prefer to write it out this way because then it's crystal clear what exactly is happening here. What it is saying here is that f is a function of g. Both are a function of x, of course. Here we have it written backwards. GOF means g is a function of f, which is itself a function of x. Now, how do we go about calculating these composite functions? All right, let's take a look at a quick example. So we have f of x is x minus 2, g of x is x squared plus 1. How do we find FOG and GOF? All right, so here's what's actually happening. Here's how we have to look at it. Let me just insert a new slide here for a second. So let me just quickly write these down one more time. F of x is x minus 2. G of x is x squared plus 1. So in order to calculate f of g of x, it's pronounced f of g of x. It's really no different than evaluating this function at a particular value. So in other words, if I wanted to know f of 3, what I would do is simply replace all the x's with 3's. So this is really no different. What you're doing instead of using 3 is you're using g of x. So since f of x is x minus 2, that means that f of g of x is g of x minus 2. I've replaced the x with g of x. Now, of course, I now have to substitute the actual function itself. I can't just leave it like this. F of g of x is therefore x squared plus 1 minus 2, or simply x squared minus 1. So it's a lot more complicated than it looks. Now, of course, if you have complicated functions, this can get very messy. But the concept is very straightforward. Instead of replacing the x's with a constant in a function, you're replacing them with another function. And then similarly, if we have the same two functions, f of x is x minus 2, g of x is x squared plus 1, g of f of x can be thought of as go to the g function, replace all the x's with f of x. Okay. So in other words, you see what I've done, where I had x squared, I now have f of x squared. So therefore I have x minus 2 squared plus 1. Now, x minus 2 squared, we can figure that out in a couple of different ways. We can try FOIL, for example. Here's f for first. X squared outer is O. Inner would be these two, also minus 2x. Last is these two, positive 4. So that expression by itself is x squared minus 4x plus 4. So now I'm going to replace all of this with x squared minus 4x plus 4 plus 1. And now, of course, I can drop the parentheses, and this is my final answer. All right. Now, by the way, Symbolab can handle this. I have to admit, I've started to forget how it works, but I know it has this capability. But as always, I find it easier to find the instructions on Google. All right. So, all right, let's see how this works. F of x, let's go back, was x minus 2. Hmm. I'm not seeing how you're supposed to enter g of x. So I know they've changed the whole interface just since the spring semester when I was using it in one of my other classes. It's very frustrating because it's not the least bit obvious to me right now what I'm supposed to do next. I mean, it does say composition calculator. No, let's try this. It used to give me a second line to type on. Is it x squared plus 1? Okay. See, the thing is, it's reading them, but now I don't see how you're supposed to ask it for the composition. Well, you know what? I run into this all the time with the technology. It's supposed they make it sound like it's so user friendly, so easy. And in fact, it's always just the opposite. There's absolutely nothing here to indicate how to do. Oh, well, maybe I got lucky. See, now here it says f of g. Again, is that what I'm supposed to do? How am I supposed to know? No, but oh, okay, maybe that was right. You see, it did come up with x squared minus 1. It just seems very strange that it does. It, it's just not accepting the information the way it used to. Well, let me try this. It doesn't have what I need for g of f of x, though. Wow, this is unbelievable. I mean, they've clearly made the product worse. I don't know what they did to it, but it's definitely worse. I I, I don't know what to do. Well, I guess that's why we can't rely on technology. I mean, you have to do it yourself. Unless I can copy this symbol, because it's clearly not available above. It just seems so stupid. Yeah. Steps are not supported. Okay. Yeah. This is why you get your hands on Mathematica, by the way. You're never going to have problems like this. It's a very professional package. It's free, and I guess that's what we should expect. All right. Anyway, never mind. Um, so we have another one here. Oh no, we're done with both of them. Okay. So I'll tell you what, just because we could probably stand some practice, let me make up a couple more just so you can see. Um, let's just say that f of x is x minus 3. I'll make that x squared minus 3. And you know what? Let's make it a little more complicated. Okay. So f of g of x would mean all of these x's are being replaced with g of x. So here's where we had an x squared, I mean, and then here's negative 3x. Okay, so the x's are being replaced. So I'm going to have 2x plus 7 squared minus 3 times 2x plus 7 plus 4. And over on the sign, we can apply FOIL here. Ooh, it's a little tight. Let me see what I can do. Okay, f would be these two terms, 4x squared. O would be these two terms, 14x. I would be here. Once again, that's 14x. Last would be these two, 49. So altogether, we have 4x squared plus 28x plus 49. Okay, so I'll write that here. Now here I'm going to distribute negative 3 across these two terms, minus 6x, minus 21, and then I have 4 here. So I'll drop the parentheses, and then what I'm going to do is combine the like terms, 28x minus 6x. And then I have 3 constants, 49 minus 21 is 28 plus 4 is 32. So that's all that one was. Now let's try g of f of x, which apparently Symbolab can no longer do. All right, so once again, f of x is x squared minus 3x plus 4. G of x is 2x plus 7. So g of f of x, this is pretty straightforward because now you're only making one replacement here. So you've got 2 times x squared minus 3x plus 4 plus 7. I can distribute this 2 across all 3 of these terms. 2x squared minus 6x plus 8 plus 7. And so I've only got 2 like terms, the 2 constants, 2x squared minus 6x plus 15. Okay. All right, and so that's that. I think we're in pretty good shape now. Now what we're going to do is try to evaluate a composite function. Now, again, this is not as complicated as it sounds. For example, what if I wanted to know the value of not just, let's say, f of g of x, but f of g of 3? What do I do now? Well, it's actually a very simple case. There's a couple of ways you could do this, but the easiest is probably to evaluate the g of 3 here, because that's going to give us a constant. And then whatever that constant is, we plug it into f, and we'll get a result. So, for example, f of x is x plus 7. G of x is 2x squared minus 3. Now, we could certainly do f of g of x and then plug in the 1. But I think it'll probably be quicker to say, all right, why don't we do this? Let's just solve for g of 1. And what that tells me is that f of g of 1 is just f of negative 1. And so that would be you're replacing the x with negative 1, add 7 to that, and you end up with 6. So it's very straightforward. And often this is exactly what we need to do. I mean, it's fine to find, the composite function, but often our goal is to find the specific value of it. And then we can try g of f of 1. Okay, so here's our f of x. Here's g of x. So because we're looking for g of f of 1, I want to start by evaluating f of 1, which you can see here is simply 8. So therefore, g of f of x is the same as g of 8. Plug in all the 8s here, and I ultimately end up with 125. Okay. So again, what do? We solve for f of 1 first. Substitute the result into g of x, and you're all set. Now, the next thing we're going to do is look for the domain of a composite function. Yes, you can always find the domain in the range of any function that you run into. It doesn't matter if it's composite or if it's just a regular function. There's always a way of doing that. So let's take a look at this case. So, by the way, I mean, I guess Simple Lab is capable of still drawing these things. I just wanted to see what they look like. Even though I've completely lost all my confidence in it. The first one is 5. Actually, it used to be the case that you could show them both at once. I don't know if that's still true or not. You could probably, I mean, you can get an idea. We did a bunch of these the other day. And, it's pretty clear that this function has a discontinuity in it because x equals 1 will lead to division by 0. Yeah, so we've seen similar functions before, except that this time the vertical asymptote is 1 instead of 0. What about the other one? 4 over 3x minus 2. You know what? Let me try something here. I guess it doesn't matter. We don't need to see them both at the same time. G of x is 4 over 3x minus 2. Again, discontinuity. So let's do this. Let's actually solve for f of g of x. Actually, this is good practice. Let's solve for f of g of x and see what it looks like. Okay. So f of g of x would be, whoops. So remember what we're doing. We're replacing all the x's here with g of x. So it'll have 5 over g of x minus 1. So this one is a bit of a mess. So what I'm going to do is create a common denominator. So that I can consolidate these two terms in the denominator. Now, here's the interesting part. What I'm going to do is rewrite this. When you're dividing by a ratio like that, you can rewrite it as the product of that numerator times the inverse of that ratio. Oh, you know what I should have done? All right, hold on. I just realized I didn't completely finish consolidating all the terms. This one here, 4 minus 3x plus 2 is actually 6 minus 3x over 3x minus 2. Okay, so now let me just copy that. So what I'm going to do is multiply by the inverse. Okay. So let's go to symbol lab and graph this. No. Oh, here it is. Okay. So we have 15x minus 10 over 6 minus 3x. And again, you can see clearly there's going to be an asymptote in there somewhere. Possibly, yeah. Oh, there's a couple of them. Yeah. So anyway, there is a discontinuity here. On the vertical axis, this would be 2. Because then you'll get division by 0. The range is everything except, it turns out, -5. We'll demonstrate that later on. The key here is this: the domain is everything from -infinity up to 2, not including the 2, then 2 up to infinity, not including the 2. So let's go to symbol lab and see what it has to say for itself. We'll take the final result. Oh, it's already there. All right. So what I'm going to do is see if I can. Oh, it says it right there. The domain is everything except for 2. In other words, the way they're writing it, it's just saying that x is strictly greater than 2, and it's also strictly greater than 2. So in other words, this is equivalent to saying it's just anything but 2. Okay. Now, here's an interesting idea. We can actually take a function and break it up into 2 components. In other words, any function can actually be expressed as a composite function. So let's take this as an example, something as simple as f of x equals radical x minus 8. You might look at it and say, well, how can we turn that into a composite function? Well, here's what we're going to do. We're going to treat this as g of h of x. This is a new function. And so what we're going to do is define h of x to be x minus 8. And then g of x is radical x. So you can see that g of h of x means all the x's in g are being replaced with h of x. So this is equal to radical h of x, or simply radical x minus a. Now, you might say, well, why would we want to bother to do this? But there might be times when this could come in handy where you can, if you may be able to simplify the solution by breaking this up into two smaller pieces. It's good to know that this kind of thing can be done. It might just be a simple matter of trying to take a very messy expression and turn it into something more manageable. That might be the motivation for doing this, but the important thing is that it can be done. So, just be aware that you can take a function and break it up into a composite function if there's a good reason for it. Now, absolute value functions, these are kind of a strange type of situation. It turns out that, of course, an absolute value function will always have two solutions. Except, well, actually, I shouldn't say that. The exception is this one. This one only has one solution. It only touches the axis at 0, 0. But for all the other ones, there's going to be two. Because remember, the whole point of this is that to find real solutions, we need to know where the function crosses the horizontal axis. Now, in the strange case where it ends up here somewhere, we're going to have two solutions, but they'll both be imaginary. All right, so there'll still be two, just not real numbers. But we're going to focus our attention on these cases. Okay, so how in the world would you find both of those solutions? Well, there's several different ways of going about this. And we have to remember how absolute values were defined in the first place. So this implies that there's a different solution when x is non-negative and when x is negative. So the question is how to find them. So if you notice here, that's the function. In fact, we can go to Symbolab and see what it looks like. Uh, 4x plus 1, absolute value of 4x plus 1, minus 7. So yes, there's going to be two solutions. Well, it just so happens that they're -2 and 3/2. Okay, but we're going to prove it. Okay. How did we find that? So we rearranged. Now, remember too, when we say we're finding the solutions of the function, we're trying to figure out where they cross the horizontal axis. In other words, we want to know where y equals 0. Okay, so we set f of x equal to 0. So what you've actually done here is set 0 equals absolute 4x plus 1 minus 7. Therefore, 7 is 4x plus 1, absolute. So based on this definition up here, in the first quadrant, or at least I should say the positives, positive values of x, we have just 4x plus 1. With the negative values of x, we have the negatives. Okay, so this is the whole thing right here. Take what you've got. The absolute value can be rewritten in two ways. The actual value of what's inside those bars goes here. That represents all the positive zeros, x's rather. And then here we have simply the negative of that. Now we can just solve for it. I mean, we subtract 1 from both sides, divide out the 4, Now here, add that 1 to both sides, divided by -4, and we have -2. So Symbolab appears to have been correct. 3/2 and -2 are the solutions of this absolute value function. In both cases, substituting either of these, in fact, you can prove it right now. In the next slide, let's just do that real fast. Let's see, absolute 4x plus 1 equals 7. We'll start with x equals -2. All right, that's correct. You just want to be careful with these absolute value signs. All right, now what about 3/2? Let's see if that one works. Okay, so that's it. That means we've done it correctly. All right, let's try another one. Now that we know the secret, so we have f of x is absolute 2x minus 7 minus 5. So remember, we're setting this equal to 0. And then what you should do is always simplify. Get everything on the left-hand side that is not inside the absolute value sign, because it'll be a lot easier that way. Just in other words, try to get everything on the left-hand side. So isolate the absolute value term. Now, what we have to do is write it out like this. And then we just solve it the normal way. And so we end up with 6 and -1. Oh, yes. No, that's right. For a fraction of a second there, I thought I goofed it up. No, it's, oh, yes, I did goof it up. It is +1. Sorry. Look what I did. There you go. All right, now we're talking. All right. So those are all the same. Now we're going to come up to a fairly challenging topic, the notion of an inverse. Now, two inverse functions essentially are functions that do the opposite. Like, I mean, just intuitively, x squared and the square root of x are inverses. Because you're whatever the one is doing, you're basically offsetting it with the second function. In other words, if I took a number like, let's say 4, and then I squared it, and then I took the square root, I would bring me right back to my original value. And I can do it both ways. So in other words, I start with 4, I ended up with 4. I start with 4, end up with 4. So the notation we'll use for inverses is F inverse, F negative 1. So what we're going to do is try to see how to find the inverse of a function. Now, it's obvious for x squared and the square root of x, but it isn't always that straightforward. In fact, it's often a very complex procedure. But it turns out there's a surprisingly simple way of doing this. So now what I just showed you here can be more formally expressed in the following way. If f and f for f of x and its inverse, the following two conditions have to hold. Number one, the composite f inverse of f of x brings us back to the original x, and here f of f inverse of x also equals x. Like I said, if we let f of x equal x squared, and we claim that f inverse is radical x, this first one is saying that radical x squared is x, and the second one is saying that radical x squared is x. Okay. And both of them have to be true, by the way. One is not good enough. All right. Now, how does one find the inverse? Oh, all right. I see. I already used this example in the slides. That's fine. The only difference is instead of writing it with a square root, I wrote it as x to the 0.5 power. That's fine. All right. How about this one? Are f of x equals 4x and g of x equals 1/4 of x inverse functions? What we're going to do now is just prove it. I didn't show you how to actually determine that these are inverses. We just want to demonstrate that this is correct. We'll start with that. So in other words, they're telling us you're going to use g of x to represent the inverse. Okay, you could write it as f inverse of x if you want. So in other words, what we have to do is prove that means that f of g of x must equal x. So we have 4g of x. I've replaced the x with g of x. So that's correct. G of f of x, 0.25 f of x. Oh yeah. So it works. Now the big question is how did we know that in the first place? In other words, imagine you're given the function g equals f of x is 4x. How did you know that 1/4 of x is its inverse? Well, the technique is surprisingly simple. Here's one. Let's try this. First of all, write it as y. It'll be a little simpler this way instead of f of x. The strange part is that what you're going to do is reverse the y's and x's. Okay, so in other words, you're going to have x is 1 over y plus 2. And all I did was wherever there was a y, it's now an x. Wherever there used to be an x, it's now a y. And then solve for y. So I'm going to multiply both sides by y plus 2. That's your inverse. Oh my God, that was so strange. reverse the x's and y's and solve for y. Oh my God. So in other words, if f of x is 1 over x plus 2, inverse of x must be 1 minus 2x over x. And now we're going to get some practice by proving it. Wow. Now Symbolab can do this too. So once again, one over x plus 2. And we claim that the inverse is 1 minus 2x over x. So we have to show two things. This must be equal to x, so what do we have here? We replace this x with f inverse of x. Now, of course, we need a common denominator. Of course, we choose x. One over x, or 1 times x over 1. Ah, perfect. So one condition is definitely true. Now we need to show that f inverse of f of x is also equal to x. All right, so let me repeat the values. F of x now I need to show that f inverse of f of x is x. So we're in the inverse, I need to replace both of these x's within f of x. Just a little bit messier. All right, so I need a common denominator up here. All right, so I'll need to move that onto the next slide. Let's see, what do we have? So what I'm going to do is rewrite that as, instead of 1 divided by 1 over x plus 2, I'm going to multiply that by the inverse. You can see these cancel out. I'm left with x over 1, which is just x. So that means that all of our work led to something important. We were able to not only find the inverse, but prove that we did it correctly. Now, sometimes you can see these by looking at their graphs. Sometimes it's not that clear. I mean, we could try it, but it's been my experience that sometimes it's very obvious when two functions are inverses, and sometimes it's not. So maybe we won't bother to look at the graphs. All right, I'll tell you. Let's just at least give it a shot, just to see if it's noticeable. I have a feeling it will not be. I'm telling. Um, it's really just I think we're just I don't want to waste any more time with this. Okay, now we'll get a lot of practice with this. We'll do many more examples when we have our first assignment. That'll be definitely one of them. So you'll get plenty of opportunities to practice. Now, this next part is just a definition. We have this concept of even and odd functions. So you can probably imagine, like, for example, look at this one. F of x equals f of negative x. So when would you see something like that? Y equals x squared is a negative, an even function because let's say, for example, f of 2 equals f of negative 2, and both of them are 4. And that's true no matter what numbers I pick for x. 3 and negative 3, for example, they're both equal to 9. So y equals x squared would be an example of an even function. Now, this one would be something like this. So let's just say, for example, I chose 2 and negative 2. 2 cubed is 8. Negative 2 cubed is negative 8. Okay, so in other words, f of 2 is 8. F of negative 2 is negative 8, which means that f of negative 2, or actually, let me write it like this. F of 2 is negative f of negative 2. And that's what it means. So, yeah, we'll run into this again. It's just the idea that there's a balance with the even functions between the negatives and the positives, which we do not have with the odds. Now, it turns out, though, that many functions don't fall into either category. In other words, these are unusual cases. You don't see a ton of odd and even functions. Most functions do not fall into either category. So let's try this. Let's see if we can identify whether this one is even, odd, or neither. So what we're going to do is start by looking at the definition of even. So f of x is this expression. That implies that f of negative x is negative x cubed. It's 2 times negative x. Now, if you notice, I'll get them together right here so you can see. So what that demonstrates is that this is an odd function. Now, we don't have to go any further because it can't be both even and odd at the same time. But if you want, you can try and see why it's not. Um, well, actually, you already can see. We don't even have to bother because remember, this is the requirement for odd. Even means so if you look at this function, you can see that f of x is x cubed plus 2x. F of negative x is minus x cubed minus 2x. So in other words, these are not equal. And that just means that it's not even. But we've already proven that it is odd. Okay, now obviously if it's odd, it can't be neither. So once we've seen that it's odd, we can rule out the possibility of it being even. If, of course, on the other hand, we can show that it's even, then we can rule out the possibility of it being odd. In terms of geometry, the odd functions, it says here, are symmetrical about the origins. In other words, if you have x cubed, it's basically saying that the first and the third quadrants are mirror images of each other. Whereas with the even functions, the symmetry is with respect to the vertical axis. In other words, what's happening here is a carbon copy of what's happening over here. So here, this is an even function and is therefore symmetrical about the vertical axis. Whereas this one is symmetrical, although it's not that obvious. You have to look at it carefully. When they say it's symmetrical about the origin, they mean the first quadrant versus the third quadrant, or the second versus the fourth. It could go either way. But it's got to be, first and third or second and fourth. All right, so let's try another one. So these are the rules right here. So here's f of x. F of negative x. So that means this, this is false because negative f of negative x be minus x squared plus 7. But this one is true. Okay, because these are equal to each other. So what we're able to do here is prove that this one is even. Okay. Now, we don't have that much time left, but I just want to briefly show you what's coming up next. And now we're getting into section 1B. So if you look at your slides, you'll see that it's A, B, C, and D. And that's because, well, it seemed logical to break it up into different pieces. So what's coming up in this next section is we're going to focus exclusively on linear functions. And this is something you're probably very familiar with. We already know that the equation of a straight line is y equals mx plus b. M is the slope, b is the vertical intercept, m is formally defined as delta y over delta x. You may have heard that explained or described as the rise over the run, but this is what we're looking at. And so what's important about a linear function is that the slope is constant. It never changes. Now, by the way, there's an other way of writing the equation of a straight line. This is the one you see the most often. This is sometimes called slope intercept form. because it shows us the slope and the intercept. But there's an alternative way of doing this, which you might recall, the so-called point slope form. Um, oh, sorry. So in other words, it doesn't explicitly show you what the intercept is. It has the slope and it has a single point. Which is y x1, y1. So when you look at this equation, it doesn't, you'd have to figure out for yourself what the intercept is. And that's one of the reasons why this is less popular, because it's easier to think in terms of the slope and the intercept, but it is possible to rewrite this equation in the following way, and you'll run into that sometimes. So the slope, as we've already seen, is the difference between the y's on the line and the x's. And as we discussed the other night, there's a couple of interesting cases. If you have a flat line or horizontal line, the slope is 0. And if it's vertical, the slope is undefined because the x's don't change. Other than that, they're all either positive or negative. Okay. And positive slopes, of course, moving up. I guess you could think of it as a northeasterly direction. And this is what a negative slope would look like. Okay. So, all right. I think that might be enough for this session. So we'll pick it up tomorrow with or more discussion about linear functions. And when that's done, I think what comes after this, just out of curiosity, oh, trig functions. Okay, yes, that definitely needs to be treated separately. But all right. So I think we've had enough fun for one day. So we'll stop right here. And then in the next session, we will carry on with our discussion about linear functions. And people are getting nervous about assignments. Don't worry, they're coming. You'll have plenty of time to get them done. I'm still working with the department to figure out what's going on with the online exams. They're not being very good about getting back to me about that, but I need to have that in place before we even think about having an exam. So, but we'll worry about that later. Right now, let's just carry on with the math. Okay, so I'll see you all next time.